Hypercomputation or super-Turing computation refers to models of computation that go beyond Turing computability. This includes various hypothetical methods for the computation of non-Turing-computable functions. The term super-Turing computation emerged in the early 1990s, with at least two independent sources noted in the literature. It appeared in talks, the PhD thesis, and even earlier technical reports of Haver-Siegelman since the early 1990s for a very particular theory, and became a subfield of computation since her 1995 Science paper. It also appears in a 1990 talk and 1991 technical report by Mike Stannett, who also published a theoretical discussion of an X-machine-based super-Turing machine in March 1990. The term hypercomputation was introduced in 1999 by Jack Copeland and Diane Proudfoot. The terms are not quite synonymous. Super-Turing computation, by Siegelman, usually implies that the proposed model is likely to exist in nature and may thus be physically realizable, while hypercomputation may be a general mathematical or philosophical idea. History. A computational model going beyond Turing machines was introduced by Alan Turing in his 1938 PhD dissertation, Systems of Logic Based on Ordinals. This paper investigated mathematical systems in which an oracle was available, which could compute a single arbitrary function from naturals to naturals. He used this device to prove that even in those more powerful systems, undecidability is still present. Turing's oracle machines are mathematical abstractions, and are not physically realizable. Hypercomputation and the Church-Turing thesis. The Church-Turing thesis states that any algorithmically computable function can be computed by a Turing machine. Hypercomputers compute functions that a Turing machine cannot, and which are, hence, not computable in the Church-Turing sense. An example of a problem a Turing machine cannot solve is the halting problem. A Turing machine cannot decide if an arbitrary program halts or runs forever. Some proposed hypercomputers could simulate the program for an infinite number of steps and tell the user whether the program halted. In particular, Siegelman showed in her 1993 PhD thesis, and later in her 1998 book, that the halting problem of Turing machines can be solved with analog recurrent neural networks. Super-Turing computation and the super-Turing thesis. In the early 1990s, Haver-Siegelman and Eduardo Sontag proved that their new computational model, the artificial recurrent neural network, could perform beyond the Turing limits. Siegelman and colleagues revealed a hierarchy of well-established computational classes that start at the Turing machine and ascend to the full super-Turing power. Clarified. Siegelman described in various publications that there are many ways to reach super-Turing computation. While first she showed the existence of super-Turing computation via analog neural networks with fixed and unbounded weights, she went on to prove super-Turing power in many varied realizable machines, including small precision-weight neural networks that receive their power from learning in analog domain, or using stochasticity, or evolving over time, or use data from environment, or systems that are Turing in any computable steps and in between change by one of the above methods. See also work in verifying properties of neural networks. Siegelman's science paper demonstrated a first step of realizing this computation, while current efforts exist by physicists and engineers to build such systems. Siegelman's recent research proves that the state space of super-Turing computation is, while the space of Turing machines is only, giving a new understanding to the Turing test. As separating spaces of different size, the theory led to better understanding of neural networks and supported innovative applications in such sensitive areas as radar registration and the control of nuclear plants. Siegelman and colleagues went further to create a complexity theory for continuous time and physical systems. As a particular example, Siegelman's group analyzed linear programming in other computer science problems, showing that analog computers can solve these faster than discrete-time computers. A recent publication reveals that Alan Turing had been searching for super-Turing computation based on brain principles, and show his suggested directions how to look for it perfectly match with Siegelman's theories. Siegelman and Sontag proposed a new computational hypothesis, whereas analog learning and evolving systems are constrained by the super-Turing computational power. Other hypercomputer proposals: a Turing machine that can complete infinitely many steps. Simply being able to run for an unbounded number of steps does not suffice. One mathematical model is the Zeno machine. The Zeno machine performs its first computation step in 1 minute, the second step in 1/2 minute, the third step in 1/4 minute, etc. By summing 1 plus 1/2 plus 1/4 plus, we see that the machine performs infinitely many steps in a total of 2 minutes. According to Chagra, Zeno machines introduce physical paradoxes and its state is logically undefined outside of one side-open period of 0, 2, thus undefined exactly at 2 minutes after beginning of the computation. Turing's original Oracle machines, defined by Turing in 1939. In mid-1960s, Mark Gold and Hilary Putnam independently proposed models of inductive inference. These models enable some non-recursive sets of numbers or languages to be learned in the limit, whereas, by definition, only recursive sets of numbers or languages could be identified by a Turing machine. While the machine will stabilize to the correct answer on any learnable set in some finite time, it can only identify it as correct if it is recursive. Otherwise, the correctness is established only by running the machine forever and noting that it never revises its answer. Putnam identified this new interpretation as the class of empirical predicates, stating, "If we always posit that the most recently generated answer is correct, we will make a finite number of mistakes, but we will eventually get the correct answer. We are never sure that we have the correct answer." L. K. Schubert's 1974 paper, Iterated Limiting Recursion and the Program Minimization Problem, studied the effects of iterating the limiting procedure. This allows any arithmetic predicate to be computed. Schubert wrote, intuitively, iterated limiting identification might be regarded as higher-order inductive inference performed collectively by an ever-growing community of lower-order inductive inference machines. A real computer can perform hypercomputation if physics admits general real variables, and these are in some way harnessable for computation. This might require quite bizarre laws of physics, and would at minimum require the ability to measure a real-valued physical value to arbitrary precision despite thermal noise and quantum effects. A proposed technique known as fair nondeterminism or unbounded nondeterminism may allow the computation of non-computable functions. It seems natural that the possibility of time travel makes hypercomputation possible by itself. However, this is not so since a CTC does not provide the unbounded amount of storage that an infinite computation would require. Nevertheless, there are spacetimes in which the CTC region can be used for relativistic hypercomputation. Access to a CTC may allow the rapid solution to PSPACE complete problems, a complexity class which, while Turing decidable, is generally considered computationally intractable. According to a 1992 paper, a computer operating in a Malamud-Hogarth spacetime or in orbit around a rotating black hole could theoretically perform non-Turing computations. The infinite-time Turing machine is a generalization of the Zeno machine that can perform infinitely long computations whose steps are enumerated by potentially transfinite ordinal numbers. It models an otherwise ordinary Turing machine for which non-halting computations are completed by entering a special state reserved for reaching a limit ordinal and to which the results of the preceding infinite computation are available. Jan van Leeuwen and Jerry Wiedemann wrote a paper suggesting that the Internet should be modeled as a non-uniform computing system, equipped with an advice function representing the ability of computers to be upgraded. A symbol sequence is computable in the limit if there is a finite, possibly non-halting program on a universal Turing machine that incrementally outputs every symbol of the sequence. This includes the dyadic expansion of pi and of every other computable real, but still excludes all non-computable rails. Traditional Turing machines cannot edit their previous outputs. Generalized Turing machines, as defined by Jürgen Schmidhuber, can. He defines the constructively describable symbol sequences as those that have a finite, non-halting program running on a generalized Turing machine, such that in any output symbol eventually converges, that is, it does not change any more after some finite initial time interval. Due to limitations first exhibited by Kurt Gödel, it may be impossible to predict the convergence time itself by a halting program. Otherwise the halting problem could be solved. Schmidhuber. In 1970, E.S. Santos defined a class of fuzzy logic-based fuzzy algorithms, and fuzzy Turing machines. Subsequently, Biarcino and G. Gerler showed that such a definition would allow the computation of non-recursive languages. They suggested an alternative set of definitions without this difficulty. Jerry Wiedemann analyzed the capabilities of Santos' original proposal in 2004. Dmytro Taranovsky has proposed a finitistic model of traditionally non-finitistic branches of analysis, built around a Turing machine equipped with a rapidly increasing function as its oracle. By this and more complicated models he was able to give an interpretation of second-order arithmetic analysis of capabilities. Many hypercomputation proposals amount to alternative ways to read an oracle or advice function embedded into an otherwise classical machine. Others allow access to some higher level of the arithmetic hierarchy. For example, supertasking Turing machines, under the usual assumptions, would be able to compute any predicate in the truth table degree containing or limiting recursion. By contrast, can compute any predicate or function in the corresponding Turing degree, which is known to be gold. Further showed that limiting partial recursion would allow the computation of precisely the predicates. Taxonomy of super-recursive computation methodologies. Mark Bergen has collected a list of what he calls super-recursive algorithms, limiting recursive functions and limiting partial recursive functions, trial and error predicates, inductive inference machines, inductive Turing machines, limit Turing machines, trial and error machines, general Turing machines, Internet machines, evolutionary computers, which use DNA to produce the value of a function, fuzzy computation, evolutionary Turing machines. In the same book, he presents also a list of algorithmic schemes, Turing machines with arbitrary oracles, trans-recursive operators, machines that compute with real numbers, static neural networks based on real weights or equivalently, neural networks of finite precision weights but with asynchronous update, stochastic coin, evolving or learning. Criticism. Martin Davis, in his writings on hypercomputation, refers to this subject as a myth, and offers counter-arguments to the physical realizability of hypercomputation. As for its theory, he argues against the claims that this is a new field founded in the 1990s. This point of view relies on the history of computability theory, as also mentioned above. In his argument he makes a remark that all of hypercomputation is trivial, as if non-computable inputs are permitted then non-computable outputs are attainable. It is widely accepted that this criticism refers to earliest mathematical and philosophical suggestions and ignores much of the newer proposals that are not subject to the criticism. Andrew Hodges wrote a critical commentary on Copland and Proudfoot's article,